here. Oh boy. Example is the point covariance between y with respect to x. And whatever. All right. So this technique like this, which is a very simple estimation based on statistical equations, are not going to be used by neural networks. But it's good to mention that you don't always need deep neural nets for every problem. Actually, you will see later on that this actually is a better approximation than the other than if you had done using stochastic gradient descent. So this is the stochastic gradient descent way of doing it. Okay, so this is the same problem, but now you have a number of epochs, you have learning rate, and based on equations here, so you go through each epoch, you go through each one of these prediction based on this is essentially weights here. This is how Jason likes writing weights, so I'll keep that way. All right, so every time, for every row of data, you try to make a prediction, and you see how far the prediction is, and then of course you adjust your weight. So this one is the weight for the bias, and these are weights for, well, um, the axis, so to speak. So yeah, the first weight is set for bias. So these are being adjusted, and of course, slowly but surely, based on the gradient, you're hoping that it will arrive to the correct to the optimal weight. And so actually, something to know that this is very small. The reason for this being so small is because um, your x variable is very large. It's in the thousands, and it give a lot of weight to this, to your errors. And if you use a large learning rate, they will overshoot your gradient, and they actually wouldn't ever converge. In fact, they actually will give you a overflow error somewhere. So if you run, oh boy, well, I think I believe you have to start. You have to reset these guys. Let's see here. Okay. Okay. Yeah, it remembers. Actually remembers. Wait, yeah. All right, so now it starts over, and probably don't really need it 200 epochs. So this is pretty close to the estimation using the simple linear regression based on the relationships. And but yeah, so you don't really have to worry about overfitting because this is very simple linear regression, linear equation that's used to estimate. Essentially, there's pretty much no way to overfit. Because there is no complexity. It's a line. All right, cool. So going off previous example, actually this I did not use the previous example. I tried to using the previous example to later on actually get what's above average and what's not above average, and it did not work as well as I'd liked it to work. It essentially says only one of the these points. Like, I mean, of course I didn't have exact points, but essentially only said one of these points are above average. I mean, below average, and that's not correct. So I decided to use the simple linear regression. But based off this is just a simple classification problem. Like you're classifying where the house is above or below the average price, and if it's one, it's above the average, and 0 being not above average or below average. So since you already know the estimate equation, you can use the I mean your iteration to I guess to classify whether a house is above average or not above average. And I think that the way to do that is that this is a linear regression, and essentially you predict that it is above average if the housing price is greater than what you predict based on the square footage. And for this, we won't be the one data, and so this one is let me just run this again. This one is price of 11, um, say 110,000, and actually this will be below the average, right? If you put it as 12, I believe it should be above average right there, right? So one thing to note, this is actually one of the examples from the classroom that you can go up to. So how do you deal with additional I guess variables? And this will be in a dimension. But here's the thing: having additional dimension is not always a good thing. There's something to think about, because you can see with this, the test and grade essentially, if a good test and good grade, you are going to have high class rank. But bad ones, you're going to have low class rank. And this class rank really doesn't really add any information to this data. And you can actually see that you can bisect this part without it being a plane. So you can reduce the number dimension here and still, it works very well. And that saves you a lot of complexity, computation, and your algorithm will just work better. So actually one of the ways to reduce dimensionality is actually the known as the principal component analysis. You can go to this link here. Generally, towards data science have pretty good and intuitive explanations for a lot of things. There's actually a lot of algorithm that does dimensionality reduction, but this is like principal component analysis, like one of the most basic understanding you should have. Okay. So although like if you are using convolutional neural networks where there's a lot of images have a lot of pixels, and PCA is not really gonna work for it, but it's worth thinking about when you can reduce the dimension. So if you see that your images doesn't really give additional information from their colors, if colors don't really matter, you really you can make it grayscale black and white, and you know it, it will reduce the dimension from, let's say, the three channels. So now you just have 2D um, data instead of let's see, 1, 2, 3, instead of what's it, 4 dimension? Yeah, yeah. Okay. So here's another thing to mention, that the classifier we used above here for the averages, it's we applied our own intuition, right? Actually, yeah, there's actually I mentioned here. We applied our own intuition, and that we knew how to calculate averages, right? We know what's above the average and what's below the average, but neural nets don't know that. Machine learning algorithm off the top of their head won't know that either, right? So so there. The next example, we're going to show how to build an example that uses training algorithm for the for for the um, for the classification algorithm to converge. Actually, the classification algorithm, put simply, actually there are known as perceptrons. And this is actually where I decided to use the this is why I've changed the above average to use the simple algorithm rather than the complex one, because when when I use a complex one, you can see this is one that's below average, this is below average, but I'll classify all these as above average. The only one that said was below average was this one, which it seemed off, right? So as you can see, like if you don't need complicated algorithms to get to a solution, it makes sense not to use them. Right. So we'll run these again. That's the averages. So actually, I added some information about one hot encoding, which I'm going to go more into next session. I wasn't able to compile that information this session. All right. Okay, so this is something else that is interesting. So this is a 400 square footage house that has a pricing of 0. You would believe that this is below average, but the algorithm is outputting that is above average. I did some thinking about this, and actually this is something I learned outside of my nano degrees. And it'll be mentioned in your projects as well. There's a specific reasons for this, right? And you will see soon. So you can see the housing average has not changed. It's just fine, right? The reason for this classification here, with it being 1, right? This is again kind of lending itself back to the housing size data being so large. Even this minuscule weights, it's just not converging. I see the error going back down, going back up, going back down, going back up, and it can't converge the correct solution there. Okay, so this so standardizing the data essentially is just you're getting the column averages, you're getting column standard deviation, and okay. R minus go. Yeah, then you are taking the taking your data set over the difference between your data set and the main over the standard deviation, which will get you close to 1. That's the goal. So once your data set is close to 1, it's much easier to work with for machine learning algorithms in general, except for tree. Trees are special, but you can learn about that on your own. Okay, so this is the so I took the housing average housing data and made them lists because this doesn't really give you back a another result. It just modifies in place, and you can't modify tuples, which was what I had originally treated them with. So I did standardization of this, right? Standardize the data, and it will look like this. But we don't want the last column to be changed, because this is our result column. This is the whether it is a 1 or 0. We don't want it to be -1 and this number, right? So so there was 2 ways to do it. Either I preserve it or I just put it back, which is what I decided to do. I taken the average house data and put it back in here. Right. So now you can see that where it is average or not is here. And then I also standardize the my test set. Or this isn't really tested. This is what I'm trying to predict, but they're just it's more or less the same thing. So this is a standardized data set of that, and now we are in the perceptron. And you can see we converge very quickly after 7 epochs. Essentially, there's no more error. And it says this is above average, which is true. And I believe if we take it down, it will be below average. Yeah. And I left a link here for additional intuition. This actually is to my to a talk I had for just the stochastic gradient descent algorithm, which I'm still going to talk on the next session, talk more about on the next session, but yeah, so next session will be for stochastic gradient. Well, no, not the rest of the introduction and starting to go into TensorFlow. Because I do believe the basics is very important. Yeah, see you next time.